And welcome to lecture 38, Fourier series and vector spaces of functions and the Fourier basis. This is our last lecture in Physics 155. We've made it all the way to the end. I'm going to talk about two things in this lecture. The first one is to reiterate some of the points of Poisson's theorem and notions of continuity. Earlier, I think it was 2 lectures ago, we showed that the separation of variables method plus expanding a function in a Fourier series allowed us to solve the heat diffusion problem for an arbitrary continuous function f of theta on the circumference of the disk. That function told us the temperature that was at each angular direction on the circumference of the disk. We found out that if f of theta was continuously differentiable, then one could show that the Fourier series approached f of theta pointwise, which means at each point theta you can show in the limit as the number of terms in the sum goes to infinity, the sum will converge and will converge to this exact value of f of theta. We also learned that in cases where the function is piecewise continuous, so it has discontinuities, this will not happen at the points where the discontinuities are due to this phenomenon that's called the Gibbs phenomenon. So it turns out there are 2 other types of convergence that we can examine for the Fourier series. One is called uniform convergence, and it says the following. We're going to work with a truncated Fourier series. We're going to call that Sn of theta, and it's just the sum n equals minus big N to big N of an e to the in theta, with an defined exactly the way it was before, the integral 1 over 2 pi, integral from minus pi to pi d theta, f of theta e to the minus in theta. And the claim is that when n is large enough, then the absolute value of Sn of theta minus f of theta will be less than or equal to some small number epsilon. Now not just at the point theta, but for all theta between 0 and 2 pi. And if that's true, then we say that the Fourier series in the limit n goes to infinity converges uniformly to the function f of theta. This is called Weierstrass's theorem because Weierstrass was the person who proved it, and if you are interested in the details of how to prove it, the proof is in the book. The other form of continuity is called least squares continuity, and for that we have a much weaker condition. All we want is the integral of Sn of theta minus f of theta modulus squared to be less than or equal to epsilon. Because it's an integral, it allows us to have things like the Gibbs phenomenon at a finite number of points, and that doesn't affect the integral at all because I can change the function value at any individual points and the integral doesn't get changed. This continuity is also sometimes called the average mean squared deviation. The proof of this is in the book, and it employs something that's called Parseval's identity, which is a very important identity that says that 2 pi, the sum of the modulus squared of the Fourier coefficients, is equal to the integral of the modulus of f of theta squared, which is an identity that is, at least when I look at it, certainly not something that is immediately obvious that it must be true. Okay, that's it for continuity. As I had mentioned before, there are even more definitions of continuity that one can come up with, and in many cases, proving whether or not a Fourier series satisfies that continuity is one of the steps along the way in analysis that people that study these things often will work on. Instead, now we're going to change and we're going to go back to a topic that we had looked at back when we were doing linear algebra and we were looking at vector spaces, where we looked at different basis functions for an infinite dimensional vector space that was given by a set of continuous functions or functions that could be integrated over a particular interval or so forth. In this case, we're going to look at periodic functions on the interval from minus pi to pi, and we're going to let un equals e to the in theta be a set of basis vectors in this space. Now, this is a complex vector space, so we're going to need a complex dot product. We've already defined what these are. The dot product of f with g is 1 over 2 pi, the integral from minus pi to pi d theta, f of theta g star of theta, where the star denotes complex conjugation. That means I changed the sign of every term that is multiplied by an I in the function g of theta. Now in particular, if I look at those basis functions and I take the dot product of um with un, what I find is get 1 over 2 pi integral from minus pi to pi d theta, e to the im theta, e to the minus I n theta. And we know, I can write that as e to the I m minus n times theta, and we know that that integral is 0 for every integer except the integer in the coefficient being 0, and that means when m equals n. And if m equals n, that exponential is equal to 1. The integral is equal to 2 pi divided by 2 pi. It's equal to 1. So we get this Kronecker delta function, delta mn. If you remember, that function is equal to 0 if m does not equal n, and it's equal to 1 if m is equal to n. So this set of functions un, where n is going from minus infinity to plus infinity, is an infinite set of orthonormal basis vectors in the space given by this dot product that we've just been discussing. So let's imagine expanding a function f of theta in terms of these basis vectors. So the first thing we need to do is we need to take the dot product of the function with the unit vector, and that, using our definition, is 1 over 2 pi integral from minus pi to pi d theta f of theta e to the minus I n theta. That's the number that we used to call capital A sub n. And then we expand the function as f dot un times un summed over all n. Well, that's just equal to the sum n equals minus infinity to plus infinity of an e to the I n theta. That is the Fourier series. It's the same function that we had before. And we know that that will actually converge to f of theta if f of theta is a smooth function on this periodic interval between minus pi and pi. And so we've actually, you might not have realized it, but showing that that Fourier series converges to this function actually shows that this basis set is a complete basis set. So it says I can describe all functions that fall under the category that we're looking at. I can describe all of those functions using this Fourier series. Okay, let's take a look at what Parseval's identity becomes in this space. It's just the norm squared, and so that's 1 over 2 pi, the integral from minus pi to pi d theta f of theta squared. That comes from the definition of the dot product. But we also know, if we plug in what f of theta is in terms of the Fourier series, we can evaluate it, and we get that it's equal to the sum n equals minus infinity to plus infinity of an squared. And that's actually what the norm is for a function written in terms of these unit vectors, because if I wrote it as a big long vector that has infinite number of entries, each of the entries is a sub n. So the 15th entry is a sub 15, and the 37th entry is a sub 37, and so forth. And the norm of that is just the sum of the modulus squared of each of those entries in the vector, and so it's obviously given by the summation that is shown on the right-hand side. So let's talk a little bit more about dot products of functions. As we just discussed before, when we have dot products of functions, which are written in this form, I'm not going to repeat what it is. I can now re-express it in terms of the Fourier series, because we know we can re-express those functions as the Fourier series. I can use the fact that those eigenfunctions, the basis vectors, are orthonormal, and I find it's just equal to the sum over n of an times bn star, and once again, that would be what I would take the complex dot product to be for a set of vectors given by an and a set of vectors given by bn, even though n runs from minus infinity to plus infinity. That's really the only difference. It looks exactly like what we did before, except it now has this infinite number of terms instead of a finite number of terms, which is what we had for most of the vector spaces we were looking at before. Now, we can then define the angle between two functions via the norm of f times the norm of g times the cosine of the angle is equal to f dot g. And we can plug in what those norms and those dot products are in terms of the a's and the b's, and we get this formula for the cosine of the angle, sum over n an bn star divided by the square root of the sum over n modulus an squared times the sum over m modulus bm squared. Now, as before, one question you might ask is this thing on the right-hand side always have an absolute value less than or equal to 1? It turns out it does, because of the Schwarz inequality. So if you remember, the Schwarz inequality said the absolute value of the sum over n of an bn star is less than or equal to the square root of the sum over n of an squared times the sum over m of bm squared. And that's all we need to verify that the right-hand side is a number between -1 and 1, which means I can define it as a cosine of an angle, and it's a well-defined object. So that's the angle between two functions when we think of dot products in terms of this Fourier basis or this Fourier expansion, and we use this integral form for the dot product. So one other thing that the Fourier series satisfies, it's a triangle inequality, and it's kind of interesting to see what that looks like in terms of the Fourier coefficients. So just to remind you what the triangle inequality says, it says f plus g is less than or equal to the norm of f plus the norm of g. And if I write that out in terms of the Fourier coefficients, is the square root of the sum over n of the modulus of an plus bn squared is less than or equal to the sum over n of the modulus of an squared plus the sum over n of the modulus of bn squared. How do we prove this? Well, it's exactly the same as before. The norm squared of f plus g squared is the norm of f squared plus 2f dot g plus the norm of g squared. That will be less than or equal to the same thing if I take the absolute value of f dot g. This is because I can only increase by taking the absolute value because f dot g could have been a negative number. Now, I use the Schwarz inequality on f dot g, which says that f dot g is less than or equal to the norm of f times the norm of g. So now I have mod f squared plus 2 mod f mod g plus mod g squared. Well, that's just the quantity norm of f plus norm of g quantity squared. Now if I take a square root of both sides, I get the triangle identity. And so we use exactly the same technique as we used before to prove the triangle identity. And when we express it in terms of the Fourier coefficients, it has this really complicated form, which is shown for you in the top right-hand side. All right, we've reached the end. We are done. Let me say so long and thanks for all the fish, as Douglas Adams would say. If you've never seen Hitchhiker's Guide to the Galaxy, it's a fun book. I encourage you to read it. It's really been a pleasure working with you during this entire year. And I'd like to wish everyone the best of luck in their future. And I will leave you with one final quote that is probably less known from Douglas Adams. My own strategy is to find a car or the nearest equivalent, which looks as if it knows where it's going, and follow it. I rarely end up where I was intending to go, but often I end up somewhere I needed to be. That's a quote from Dirk Gently, Holistic Detective. And I encourage you to read one of those books. It's really quite a funny book, and you'll understand what that quote means if you get a chance to delve into that. And so with that, we are now completely done. You still have some work to do in class, and we also have a final exam that we have to complete. And with that, best of luck to everyone, and goodbye.